Right, question 15, the swimmer one. Okay, starts off very easy. Yeah, you're never going to see anything like this, as easy as this, I think, in a real, or easier than this in a real A level. But anyway, work done equals force times distance. Yeah, the force is 65 newtons, distance of the stroke 1.4. Do not, under any circumstances, write down equals 90 joules. Write down the real value, please, what it says on your calculator. Okay, now we want the power down, don't we? So the power is the rate at which work is done. So the total work, well, we've got 55 strokes, and the time taken in seconds, well, it's per minute, isn't it? So it's 60 seconds. That comes out as 83.4 watts. Okay, right, gets a bit trickier now. Two glides, 1 and 2. So it's just a glide. You're pushing away and you're not paddling. You're not kicking your legs. You're not using your arms. You're just literally gliding through the water. Because of the water resistance, you're going to slow down rapidly. Okay? Right, we need to explain the difference in the two graphs to describe and explain the motion of the swimmer. Okay? Right, well, as we can see, glide 2, he's slowing down more rapidly, isn't he? Okay, his velocity decreases more rapidly. Reason, well, he's less streamlined. He's got more surface area, so he's going to have a bigger resultant force from the water slowing him down. Okay, in glide 1, he's more streamlined. He's got less surface area, so he's going to slow down less rapidly. Okay, now if you have a look at the mark scheme, okay, so there's the stuff there. A lot of you missed out, or you didn't get the one about, okay, the gradient decreases, doesn't it? Yeah, the velocity is decreasing, or the swimmers are decelerating, but not a lot of people got the gradient one here, right? So it's the gradient starts high, and the gradient ends up lower. Reason for that is, well, he's slowed down, isn't he? As you slow down, water resistance slows down as well. Or water resistance decreases as well. Okay, so there's quite a lot to talk about there. Right, this one. So we've got the equation. Now, it's given us, it's something called drag coefficient. You don't know what that is. You're not seeing that, but it's a quantity that's just thrown in there. But it doesn't matter. You just need to know. You just need to show that it's a quantity with no units. So drag force, okay, drag force equals a half C rho A V squared. Right, so force is newtons on the left. Okay, so that's going to be equivalent to, forget the half, right, units of drag coefficient. Right, we've got rho. Rho is density, so that's mass per unit volume. Mass per unit volume. Okay, A is area. Area is m squared. V is speed, so that's going to be ms to the minus 1. Don't forget to square it. Okay, right, so this is now, we can just tidy this up a little bit. Okay, or rather than doing that, we could just say, right, what's this slot equal to? Now we've got kilograms, m to the minus 3, m2, m2. Just m, isn't it? M to the minus 3, and then we've got a squared and a squared, which is m to the 4, leaves m. And we've got s to the minus 1 squared, so that's s to the minus 2. Now that is the base units of the Newton. Force equals mass times acceleration. So that is equivalent to newtons. So this fella must be unitless. Last question. Suggest and explain an additional measure that a swimmer could use to reduce the drag force on him. Right, okay. A lot of you, well, obvious ones would be to become more streamlined. Okay, to become more streamlined. If you look at Olympic swimmers, professional swimmers, a lot they have these like these tight fitting swimsuits that reduces drag. Professional swimmers actually shave their legs. Even the men shave their legs because obviously every little counts in swimming. You're talking about hundredths of a second to win a race. So yeah, wearing swimming caps as well. Okay, we need to be thinking about really going down the getting more streamlined here. Okay, quite a few of you went down the route of saying, how can we change the viscosity of the water, which you're not going to get? That's not usually an option for a swimmer in a race, is it? Okay, you're not at the Olympics just before the race. Hang on a minute, I just need to change the viscosity of the water. No, that's not ever going to be an option. Some of you actually said, yeah, change the temperature of the water or come back and swim later on in the day when it's when it's going to be when it's going to be hotter because the water's hotter, it's going to be less viscous. Yeah, the physics stands up, but in terms of the context, it doesn't. Okay, if you're a swimmer and you're sort of calculating the drag force and how that's going to affect you, yeah, changing the viscosity of the water is unfortunately not going to be an option to you. Right, so there you have it. Question 15.